Hi everyone, welcome to my channel. I'm really excited about today's video because I'm going to walk you through one of my favorite deep learning projects, Twitter sentiment analysis. This project combines natural language processing, data cleaning, and neural network modeling to detect whether a tweet expresses a positive or a negative emotion. So, what exactly is sentiment analysis? In simple terms, it's the process of teaching a computer to understand human emotions in text. Every day, millions of people post tweets about movies, brands, products, politics, and events. Reading and classifying all that by hand would take forever. That's where artificial intelligence comes in. By using machine learning models, we can automatically identify whether people are happy, sad, angry, or satisfied just from the text they type online. For this project, I used the famous Sentiment 140 dataset from Kaggle. It contains 1.6 million tweets collected from real users, each already labeled as either positive 1 or negative 0. The dataset was perfect because it's large, balanced, and widely used for benchmarking sentiment models. My goal was to compare several deep learning architectures and see which one could classify tweets most accurately. Before we can train any neural network, we need clean, consistent data. Tweets can be messy, full of URLs, hashtags, mentions, emojis, and random punctuation. So my first big step was text preprocessing. I removed all the links, user mentions, and hashtags. Then I converted everything to lowercase so that words like happy and happy would be treated the same. I also removed duplicate tweets and extra spaces, keeping only the meaningful words that carry sentiment. Once the text was clean, I used the Keras tokenizer to convert each tweet into a sequence of numbers. Every unique word gets a unique integer ID, and the order of words in the tweet is preserved. Then I padded the sequences to a fixed length. I chose 80 tokens, so that all tweets have the same shape when fed into the network. This is a really important pre-processing step because deep learning models expect uniform-sized inputs. Now let's talk about the models. I experimented with 5 deep learning architectures: RNN, GRU, BiLSTM, CNN, and GNN. Each one approaches language in a slightly different way. The first model I built was a simple RNN, or recurrent neural network. It reads the tweet word by word and learns patterns based on word order. It's the most basic type of sequence model. The problem with simple RNNs is that they have trouble remembering information from far back in the sequence, so their understanding of long sentences is limited. Next, I tried the GRU, which stands for Gated Recurrent Unit. This model adds special gates that control what information should be remembered or forgotten as it moves through the sequence. GRUs are faster to train and handle longer dependencies better than a basic RNN. Then I built the BiLSTM, or Bidirectional Long Short-Term Memory Network. This one reads the tweet from left to right and also from right to left at the same time. That means it can understand context from both directions. For example, in a phrase like not really good, a BiLSTM can see that the word not changes the meaning of good. After that, I added a CNN, or convolutional neural network. You usually see CNNs in image processing, but they also work well with text. The convolution filters slide across the sequence and detect small word patterns or local features, like very good, not bad, or so angry. It doesn't care where the pattern appears, it just picks out the strongest emotional clues. CNNs are usually faster than recurrent models and very efficient for short texts like tweets. Finally, I experimented with a GNN, or Graph Neural Network. In a real GNN, words are represented as nodes and their relationships form edges, allowing the network to understand complex connections. In my simplified version, I simulated this idea with dense layers that model interactions between word embeddings. Essentially, it lets the model learn how words relate to one another beyond just their order. All the models shared a similar structure. An embedding layer that transforms each word ID into a dense numeric vector, followed by the hidden layers specific to that model type. And finally, a dense output layer with a sigmoid activation to produce a value between 0 and 1, where 0 means negative and 1 means positive. I used the Atom Optimizer for training and binary cross-entropy as the loss function because it's ideal for binary classification tasks like this. I also monitored accuracy as the main metric. To make sure the training didn't overfit, I used early stopping and reduced the learning rate when the validation loss stopped improving. Each model was trained for about 5 to 10 epochs with a batch size of 256. During training, I kept an eye on both the training and validation accuracy curves to ensure the models were learning steadily without memorizing the data. After all the models finished training, I compared their results. The simple RNN achieved around 76% validation accuracy. The GRU did better with about 80%. The BiLSTM reached 83%, and the CNN came in around 79%. The top performer was the graph neural network, which achieved 84% validation accuracy and 86% on training data. So why did that happen? The RNN struggled because it forgets long-term dependencies. The CNN worked great for shorter patterns, but couldn't always capture full context. The GRU and BiLSTM handled longer text dependencies much better, and the GNN went even further by capturing relational information among words. That's why it slightly outperformed the rest. I didn't stop at just numbers. I also visualized the dataset to get a better sense of what was going on. I created word clouds for positive and negative tweets. The most frequent positive words were love, happy, awesome, and great, while negative ones included hate, bad, and worst. I also looked at the distribution of tweet lengths. Most tweets were under 30 words and generated confusion matrices for each model to see where misclassifications occurred. These visualizations gave me insight into which words drove the predictions and where the models still got confused. If we summarize all the findings, the RNN performed the weakest because of vanishing gradients. The GRU provided a good balance between accuracy and speed. The BiLSTM gave excellent results by learning from both directions. The CNN was fast and very effective for local features, and the GNN outperformed all of them by learning deeper relationships in the text. From a practical standpoint, a system like this has many real-world applications. Companies can use sentiment analysis to track public opinion about their brands. Movie studios can measure audience reactions. Politicians can monitor how voters feel about new policies. Even researchers can study how sentiment spreads across social networks. The possibilities are huge. This project also taught me a lot about the importance of pre-processing and model choice. Clean data made a massive difference. Tokenization, padding, and lower casing might sound basic, but without them the models simply wouldn't converge properly. I also learned that no single model is perfect. Each has trade-offs between accuracy, speed, and interpretability. In the future, I'd like to extend this work using pre-trained embeddings like GloVe or Word2Vec, or even fine-tune a transformer model like BERT on the same dataset to see how much performance improves. Transformers are state-of-the-art in NLP, and it would be interesting to compare them against these more traditional architectures. Overall, I'm really happy with how this project turned out. Building and comparing these 5 models gave me a deeper understanding of how neural networks process language and how small architectural changes can make a big difference in accuracy. So that's my complete deep learning pipeline for Twitter sentiment analysis, from raw tweets all the way to an evaluated model. Thank you so much for watching. If you enjoyed this walkthrough, please give the video a thumbs up, share it with anyone interested in AI or data science, and don't forget to subscribe to the channel for more project breakdowns like this. If you have any questions or want me to explain a particular model in more depth, drop a comment below. I'd love to hear your thoughts and help out. Thanks again for tuning in, and I'll see you in the next video.